Now remember that energy is keep on decreasing as R increases because this is inversely proportional. The greater, the smaller. If you move closer to this the charge, this will be this in the energy is keep on increasing. So again, when you compare the two energy, this initial is greater in magnitude compared to the final energy. So very simple. Now what if given the electric field at this point and this charge, okay, you can use this formula. So you can say Q naught. This is you have to use this Q naught because you are talking about the energy at this point. So do not use Q. It should be the moving charge at that point, and the electric field also must be at that point. And the R is the distance from the source charge. The stationary charge is the source of the electric field. So therefore, it should be QER. QER. Now in the final, you have Q naught EB RB. These are the ways to calculate the energy at any point. Okay, this is only for what? This is only for a single charged particle. Now what will happen if there are two or more? What will happen if you are asked, what is the electric potential energy of a multiple charged particle? Suppose daghana, if we have this two or more, so we call this as a multiple charged particle. Now, what will be the energy at points on the surrounding charges? So, for example, you are asked, how much is energy at this point? Due to this charge and due to this charge, what will you do? Okay? Suppose the particle is moving from point A to B. For example, Q naught is moving in this direction. By the way, if you are asked to find the energy or the work done by take note, work done by the charge of the particle is a negative change in potential energy. So therefore, the work done by that charge does not depend on the path or or how it arrives at that point. It doesn't matter. Okay? What is needed is the change in potential energy. Okay? So therefore, regardless of what kind of curve or maybe a straight or as long as this is initial and final, the work done is the same. Okay? So suppose this is moving this curve. Okay. So therefore, we have this in order to calculate the energy at point A, you have to take note there are two interacting charges. So therefore, you have to add algebraically. Okay? You have to add algebraically. So the energy at point A is the sum of the energy produced by the two charges. So therefore, you have to add the energy at point A due to charge 1 by the energy at point A due to charge 2. So you can use this formula. Now take note that energy can be positive or negative. How when or what is the possibility of having negative of this energy? Answer is if one of these charges from the formula is negative, then the algebraic sign must be negative. So therefore, the energy must be of negative. So in this case, A to Q1, or Q naught to Q1, positive, positive, the energy is positive. But this one, Q naught to Q2, negative, then this will produce a negative energy. Okay? So depending on the sign. So therefore, do it the same. At the final point, we need to add the potential energy at point B due to charge 1. Then added by the potential energy at point B or the final due to charge 2. That's it. As simply as that. So what are the requirements in order to provide the energy at point A due to charge 1. We need the position at point A away from charge 1. Okay, so assign that as RA1. RA1 means the position of A from charge 1. And this one, we need this position, and we call this as the position of A away from charge 2. Okay? So therefore, we can now solve the energy at point A using the formula 1 over 4 pi permittivity Q1 because this is charge 1 and this is Q naught because moving over RA1. RA1 again is the position of A away from charge 1. Then added by 1 over 4 pi permittivity Q2 because this is charge 2 multiplied by the Q naught because this is the moving divided by the position of A away from charge 2. So this one is the RA2. So then, that's it. Now, in the final, okay, we need this position. The position of B away from charge 2 and the position of point B away from charge 1. So, do it the same. 1 over 4 pi permittivity Q1. Q1, because this is the charge interacted by Q naught, okay, divided by this distance away from them. Then added by the energy of this charge produced on charge B. So this should be 1 over 4 pi permittivity. Interacting charges are Q2 and Q naught divided by the position of the or the distance of B away from charge 2. So therefore, that's it. We are producing initial and final potential energy. So if you take the change of this final minus initial, okay, then take the negative sign, the negative change, it is the work done by the electric potential energy from point A to point B travel. Okay, so therefore, what will happen if there are 3 or more? What will you do? How will you compute the energy at this point and this point also? If there are 3, then you have also 3 terms here. So you have to add the 3 energies produced by the surrounding 3 charges. If there are 4, then this will become 4 terms also. So therefore, in short, the potential energy for a multiple charge particle is just, take note that this is common. We can take it out. Okay, common is the Q naught over 4 pi permittivity, leaving what? This is Q1 or charge 1 over RA1. And this is Q2 over RA2. If there are charge 3, Q3 over R3, Q plus Q4 over R4, and so on. Okay? So this is the formula for a multiple charge particle in calculating electric potential energy. Okay, so here comes the example. In order to apply the concept introduced a while ago, we will solve this problem. A point charge Q1 has a positive charge of 2.4 microcoulomb is held stationary at the origin. Okay, so if this is the Cartesian, according to the problem, there is charge 1 located at the origin with a charge of 2.4 microcoulomb. So this is stationary according to the problem. Now a second point charge, okay, a second point charge Q naught or Q2 is negative 4.3 microcoulomb moves from point X. So this is a moving based on this problem. Now take note, this is 4.3 and this is 2.4. This is greater in magnitude compared to that. Okay, but this charge was held constant. Okay, was held constant while this one is moving charge. According to the problem, this charge negative starts from the initial position of 0.15x and y is equal to 0. So therefore, this is along positive. So this must be 0.15 and the y is 0. So this is lying along x, positive x-axis, at a distance of 0.15 from the origin. Problem says that this charge moves in the final position of 0.25 meter and y is also 0.25 meter. So this is found in the first quadrant, positive, positive. So therefore, this is the position. The position RA means 0.15. Then this will move through what? Through a coordinate of 0.25 x and 0.25 meter y. Okay. So this is the position. The final position is RB. Okay. So this is the initial and this is the final. And this travels from initial towards the final. So the question is, how much is the work done by this electric force? What is the work done of this electric force? That's the question. Okay? So to answer is, you have to recall the derived formula. What is work done by electric potential? Okay? What is work done by the potential? This is the formula. The work done from A to B is a negative change in electric potential energy. But what is change? Change means final minus initial. The word change means it is always final minus initial. Our final is UB and UE is our initial. So take the change of that, then take note, negative change here. So therefore, all we need to do now is find the energy at point B and energy at point A. We have to compute the energy here and the energy at the final. So energy initial is UA, energy final is UB. So what is UA? UA. This is 1 over 4 pi permittivity multiplied by the charge 1, okay? And this is charge 2. By the way, correct this. This is charge 2. The Q naught is, our Q naught is charge 2. And this is charge 1. So this must be 2.4 while Q naught is negative 4.3 microcoulomb, where RA is 0.15. So therefore, substitute the values. This 1 over 4 pi permittivity is approximately 9 times 10 raised to 9 Newton meter square per coulomb square. While the 2.4 micro, okay, you have to convert this into coulomb. Why? Because the unit of electric constant is Newton meter square per coulomb square. So to convert the 2.4, okay, to convert the 2.4 micro is to multiply 10 raised to 6. If you multiply 10 raised to 6, you are converting the micro coulomb to coulomb. So therefore, this will becomes coulomb already. Now multiply by the second charge. The second charge is a moving charge. This is negative 4.3. You have to consider the sign. Take note, we are calculating scalar quantity. So we have to include now the sign. So 4.3, because this is micro, then therefore we have to multiply 10 raised to 6. By the way, if this is nanocoulomb, 10 raised to negative 9. Okay? That's how to convert easily. So therefore, we are now to cancel the coulomb square because numerator. So what is living in the constant, we have Newton meter square. And this one, oh no, okay, Newton meter. And this one is R, and this is meter, so meaning we cancel 1. Okay? So the remaining unit is Newton meter, and it is joule. Okay? So therefore, this is negative because this is negative sign, 6.6192 joules. Okay, the energy final is, look at this one. This is 1 over 4 pi permittivity. Okay, then the product of the two charges, the Q, sorry, change this to Q2. Okay, this must be Q2. Charge 2, this is negative 4.3 and this is ano? Okay, so this is correct. Sorry. At in the final, we have 1 over 4 pi permittivity. The interacting charge at this point is the same, di ba? This is negative 4.3 interact to 2.4. So therefore, by the way, we need how much is this position? Because we need this one, just like this one is, we did not calculate because this is already 0.15 along x. But this one, we need to use the Pythagorean theorem because this is forming a right triangle. This one is 0.25, okay? And this one is 0.25. This is 90 degrees. And this will serve as hypotenuse. So to compute for the hypotenuse is to take square root of the square of the two sides. Okay? The side, vertical side, horizontal side, take square. Then the answer is the distance of the final position away from the point charge, nearest charge is 0.354 meter. Okay? So therefore, this is the position, final position. Then you have to replace, substitute it here. Okay? The 1 over 4 pi permittivity again is 9 times 10 raised to 9, the same unit. The same because this is charge 1. Then therefore, and the same charge. Okay? The same charge. And it differs with what? Differs only with the position, RB. Okay? So therefore, okay, so calculating the result, this will result negative 0.2624 joules. Negative again because this is negative and this is also negative. So therefore, next is we have already this value. So substitute it here. Take note negative change. Then quantity final minus our final is RB UB. So 0.2624. Then minus because this minus. Then calculate. The answer is negative 0.3568 joules. This is the answer to the problem. The work done is negative. Okay? So the work done is negative because we substitute everything here, and these are the results of the change in electric potential energy. So therefore, our final answer is negative 0.3568 joules. And this answers to the problem. Okay. What will happen if we have, this is the last problem to be solved for this video. Now, we need to solve also what will happen if there are two charges. Okay? We call this as a multiple charges point. So we have, suppose we have a dipole. Problem is, this is a dipole. 3 nano coulomb and this is negative 3 nano coulomb. Now the problem is that the mass is 5 times 10 raised to, by the way, this is 9. This is, change this to 9. Okay, change this to 9, negative 9 kilogram. Forget this one. And the charge 2 nano coulomb starts from rest. This is the charge starts from rest, then moves. So this is now the situation. We have this dipole and we have this charge A at a point A, and this is point B. This charge having a magnitude of 2 nano coulomb moves from rest, start from rest at A, then move towards B. Okay? Now take note that this is positive and this is also positive charge. This is positive charge, 2 nanocoulomb. So this will repel. And due to this charge, this will be attracted. So therefore, this charge will move in this direction with velocity. If it starts from rest, there must be a final velocity here. So that's the question. What is its speed at point B? So how will you answer? Okay. So therefore, this charge 2 nanocoulomb moves from A to B. Start from rest, then it will move. In the final, how much is the final velocity? Okay. So what will be our solution? Now take note that the problem says that what is the final velocity. So therefore, what formula we derived before that relates the velocity of the particle. You remember? Okay. Now, take note that there are 2 points of travel. Starts from A, end with A. If we apply the conservation of energy, energy must be conserved, which means that the total energy at point A must be the same total energy at point B. So therefore, conservation of energy, energy A must be equal to the total energy at B. But what is energy? When we say A in physics, energy means it is the total energy. But there is kinetic energy and we have the potential energy. If we sum up the kinetic energy and potential energy, we call that as the total energy. That is the meaning of E. So therefore, expanding this one, the energy A is equivalent to kinetic energy A plus potential energy A is equivalent to the kinetic energy B. Sorry, change this to B again. This is typographical error. This is KB. Okay. So this must be KB and this is UB. Okay. So this is kinetic energy initial and this is the potential energy initial. This is the kinetic energy final and this is the potential energy final. Okay? So, take note that that the initial velocity is 0. Okay, then the distance of A from the charge 1 is RA1, while the distance of charge B, charge 2 from A is RA2. So therefore, we can calculate the potential at point A. So therefore, in order to answer this one is we need these values, the four values, the kinetic energy initial, the potential energy, the kinetic energy final, and the potential energy final. So first we will solve the potential energy initial, U sub A. The formula, because this is multiple, no? So therefore, the moving charge over 4 pi permittivity multiplied by the sum of the ratios of the charge is to distance. So charge 1 is to its distance RA1, then plus charge 2. Okay, we are talking about this point. Forget first this point. What is the energy at this point? Multiple charge, because this is positive and it's negative. So all you need to do is to take the common. The common is we have here Q naught. Okay, so Q naught over 4 pi permittivity multiplied by charge 1 over RA1, then added by charge 2 divided by RA2. The RA2 is coming from here towards this point. Okay, so then substitute. This is the constant and this is the moving charge. This is your charge 1 over RA1. RA1 is 1 cm. But 1 cm again convert to meter. It should be 10 raised to negative 2 because centi means 100. It is 10 raised to negative 2. If this is melee, 10 raised to 3. Okay? So therefore this is the charge 1 over RA1 added by charge 2. Charge 2 is 3 negative divided by the RA2, which is happens to be 2 centimeters. Okay, this is only 1 centimeter, while the other is 2 centimeters. So therefore, this should be 2 times 10 raised to negative 2 centimeter to meter. Okay, so therefore, calculate. The answer is positive 2.7 times 10 raised to negative 6 joules. Now, the energy in the final, the energy in the final should be, again, another multiple charge. It should be the energy due to charge 1 added by the energy due to charge 2. So therefore, use the formula, the same Q naught over 4 pi permittivity, and this is charge 1, okay? So we need what? We need distance. What is the distance of charge 1 away from point B? Okay? It should be this one. And this is 2 centimeters. While the other is, the charge 2 is only 1 centimeter. So therefore, when you look at the solution, this is, again, this is the constant, while this one is the moving charge, and this one is the charge 1 divided by 2 centimeters. Okay, this is 2 centimeters again. While the charge 3 is now only 1 cm. Then the result is a negative 2.7 times 10 raised to negative 6 joules. Okay? So we have already the initial potential energy and we have the final potential energy. So we need kinetic energy initial and kinetic energy final. So the kinetic energy initial is 1/2 mv squared. And this is the velocity initial. But take note, this is 0. So therefore, the kinetic energy must be 0. Okay? So, what about the final kinetic energy? The final kinetic energy is 1/2 mv squared. This is the final velocity squared. Okay? So, the mass, take note, is 5 times 10 raised to negative 9. Mass is 5 times 10 raised to negative 9 kilogram. Okay, substitute it here. Okay? Then, take note, this is unknown. So, leave it as unknown. So, we come up with 2.5 times 10 raised to negative 9 v squared. Don't worry because this is unknown. Okay? So, therefore, substituting it here in our conservation of energy equation, Ka, 0, Ua, 2.7 times 10 raised to negative 6, Kb, the final kinetic energy is 2.5 times 10 raised to negative 9 v squared. While the final energy, kinetic, or electric energy, is negative 2.7 times 10 raised to negative 6 joules. So therefore, substituting everything here, the unknown is this one. Okay? So transpose that, divide both sides by this one, take square root, okay? Then calculate. The answer is 46.48 meter per second. This is the speed of this particle in the final position. It starts from rest with 0 and it accelerates. Okay? There must be an acceleration because of the force. So therefore, there must be a final velocity. And the final velocity is equal to 46.48 meters per seconds. Okay? So, this is the answer to this problem. Okay, so to have a summary, this topic, take note that we are providing the formula for the energy for a single charge. So, the definition is 1 over 4 pi permittivity, the source charge or the stationary multiplied by the moving divided by the distance. For a multiple charge, you have to add or you have to multiply, okay, the moving charge by the constant, then the charge multiplied by the charge over the distance away from that point plus another charge and this and consider its distance from that charge from that point, then another charge and so on. So that is the energy with a multiple surrounding charges. Okay, so that's all. Thank you. The next topic is talking about the electric potential. Take note, this is electric potential energy. And we have another physical quantity, the electric potential. And it is talking about volts. So, we are about to study how to produce voltage. The voltage requires electric potential. So, if we have two potentials, what is now the potential difference? And the potential difference is voltage. And that electric potential can be obtained using electric potential energy. Okay, so see you on the next video. Thank you.